gonna be out of here by 11:45, whether the talk is done or not.
We hope they don't record it along the road.
Yeah, exactly. So I'm very excited to have as our seminar speaker, Dr. Francisco Mercado. Dr. Mercado is a CPP alum, getting his bachelor's degree from here, the very university in 2017. So it's very exciting to have him back. He then went on to UC Irvine, where he got his master's in 2019, his PhD in 2023, working with my PhD advisor, James Boyd. And he is now a National Science Foundation MPS Ascend postdoc fellow and has a joint appointment at CalTech. And he's here to tell us about really exciting things having to do with whether it's nature or nurture and how that affects galaxies. So thank you so much.
I'm very excited to be here today. As mentioned, yes, I did graduate here in 2017. Been a few years since then, so I'm really happy to be back seeing some faces. So today I'm going to talk a little bit about how sort of internal and external properties really shape the interiors of galaxies. And so that's why I named this nature versus nurture. But before I get started, this decides to work. There we go. I want to talk a little bit about some superstars that came out of this department that are still my friends today. A little bit of a history here. So this is a picture from my very last day of classes here at Cal Poly. And there are a couple of folks here in this picture that I were in my class, in the class after me. On your very left here is Lauren Kim, who just recently received her PhD from UC San Diego Scripps Oceanography Institute. And then we have Jose Flores Velasquez here, who we unfortunately lost tragically in 2019, but would have been finishing his PhD this year at UC Irvine. And on the very right, we have Dahinder Jain Singh, who earned his PhD from Ohio State University. Absolute machine of a man. Dahinder is amazing, and I'm sure many of the faculty here can attest to that. And there's me right there in the middle. You can tell that I'm like probably the least put together of this group. That's just what it is. On the right is a picture that's taken more recently at a conference that just happened a couple of weeks ago at Carnegie Observatory. This was a galaxy formation and evolution in Southern California. Took a picture with a couple of other CPP alums. On the left-hand side, you have Natalie Nicole Sanchez, who earned her PhD from University of Washington, and Evan Nunez, who is set to earn his PhD in the next several months from CalTech. And as you can still see, I'm still the least put together of the group. Things just like never change, right?
Also, Evan is our next seminar speaker in 2 weeks.
Evan is the next seminar speaker. So you'll get to chat with Evan. Evan is a great guy, awesome. So these are just a few folks that have come through this department. There are many, many more that I just could not find pictures of. So I wanted to just show you all a little bit of the connections that I do have with this department. Professor Wheeler did also mention that we intersected slightly at UC Irvine. I could not find a picture of you, unfortunately. I wish I could have. But fun fact, Coral was one of the first people that started me with running some of these simulations. So it's really, really awesome. Like my first summer at UC Irvine. So really well connected here. I'm really excited to be here. But let's go ahead and get started. So just going to give you all a quick little outline of what I'm talking about today. Going to give you all a quick little introduction of what questions I'm interested in answering and how. I'm going to talk about sort of the nature aspect of this work, which is mostly some of my past work. Then I'm going to move on to some of my current work that has to do with nurture, with how these external processes affect galactic interiors. And if there's time, I know there's a sort of drill at the end of here. So if there's time, I will want to talk a little bit about the Astro Uplift project, which is part of my NSF proposed broader impacts work. I'm really excited about that. So if we do have time, I'll get into that. If not, we have time and lunch that I can chat with some of the students about. But great, so as I kind of alluded to today, I'm very interested in determining how sort of internal processes versus external processes really shape galactic interiors. And so some of the processes that are involved here are feedback from star formation. So when stars go supernova, they inject a lot of momentum and energy into their environments, and this really, really changes the interiors of the galaxies. Another process is AGN feedback. You get this feedback from black holes. They do end up spewing out these massive jets in some cases that really, really shakes up the inner regions of galaxies. Now, a couple of external processes that you can imagine here are interactions between a galaxy and its environment, right? Galaxies are kind of like humans, right? Your sort of experience is different if you live in sort of a city compared to if you live in a more rural region. That's exactly the same for galaxies, and so these processes really affect the galactic interiors. And then finally, you also have effects from cosmic ray ionization from the first light in the universe. So if you put all of this together, you get something pretty wild, right? So what you're going to see here is just a quick video of a galaxy much like the Milky Way forming over time. You're going to see quite a few things. I should say that this is an example of a simulation that I work with. Again, it is of a galaxy that's roughly the mass of the Milky Way. It's a simulation from what we call a fire collaboration, which I will get into in a little bit. But what you see here, you see these sort of like plumes, these things getting ejected. All of this is really changing the interior of the galaxy, and that's coming from sort of star formation feedback, this sort of supernova feedback that I talked a little bit about. And you get that feedback really, really changing the interior of this galaxy, making things really complex, right? So this is part of the nature, something that comes from within, right? But once you get further on in time, you're going to start seeing this galaxy start to interact a little bit more with its environment. So you see a galaxy sort of coming into frame a little bit right now. And so these galaxies are also merging with their sort of companions. You start seeing some flybys, you start seeing some mergers, and that again also changes the interior of this galaxy. And so I hope after this video, what I've convinced you is that galaxies are very, very complex systems with many, many processes really affecting their interiors. While these galaxies are complex in nature, they do follow very tight scaling relations between their observed properties. So I'm just going to flash a few here. This is the Tully-Fisher relation, which connects the asymptotic velocity of a galaxy to its brightness. The gradient strength galaxy age relationship, which connects the strength of a galaxy's metallicity gradient to its stellar age. The mass metallicity relation, which connects the mass of a galaxy to its metallicity. And then finally, the radial acceleration relation, which connects the observed acceleration of a galaxy and its acceleration due to the bearing of it.
Make it worth mentioning that, tight is somewhat in the eye of the beholder for astronomy, and particularly this type of astronomy.
Yeah.
Yes, having something that shows a correlation on the log-log plot is absolutely a correlation that we do a lot with. I would think the experimental physicists in the room would think that's not particularly tight. We wouldn't want to see that come out in our lab.
Yes, yes. But when it comes to something as I mentioned, complex as galaxy formation, this is sort of as good as it gets. I mean, you can see something pretty tight on the top, right? But understanding how sort of these external and internal properties dictate where a given galaxy lies on these relationships can really help us answer the question of how galaxies are forming, right? And that's exactly the question that I want to answer. I want to really determine the role of internal versus external processes on setting the galaxy's position on a given stellar stage. That's sort of what the big question that I intend to answer little by little. Now, in past work, I focused on these two specific scaling relations, the gradient strength galaxy age relation and the radial acceleration, using simulations to figure out how internal properties, right, internal processes, primarily in nature, how they really shape these scaling relations. Now I'm going to focus on that a little bit before I move on to the nurture. But to answer this question of nature, these internal processes, I use what we call zoom-in simulations. We all just saw an example of a zoom-in simulation. It is just that. It is zoomed in on a particular galaxy, and we're really tracking how that galaxy is coming together over time. So I'm going to talk a little bit about what FIRE simulations are. So FIRE stands for Feedback in Realistic Environments. And this collaboration has a suite of high-resolution zoom-in cosmological simulations that do a really good job at tracking different things, as well as simulating resolved multi-phase gas components. We also track the metallicity for 11 chemical species for stars and gas. We track how stars form, so they form in dense self-gravitating gas. And then finally, we also simulate energetic feedback. Right? And so here on the right are just a few examples of some of the Milky Way-like simulations that I've worked with in the past. As you can see, they're all pretty awesome looking. It's really nice to see, pretty to sort of stare at. So these are the simulations that I've worked with in some of my past work. So the first sort of paper that I published at UC Irvine that I alluded to earlier had to do with understanding how the metallicity gradient of low mass galaxies form. Because of the time today, I'm not going to go too much into it, but in that paper, we predicted a new scaling relation, this gradient strength galaxy age relation, which really tells us that as a galaxy evolves and you have more of these sort of star formation feedback events, the inner region of the galaxy will change enough to form these steep gradients. I can talk a little bit more later about how that actually happens, but the result of this is that the gradient strength galaxy age relation of the GSGA arises as a result of internal feedback processes, right? This is the nature of the galaxy, right? An environment really plays a smaller role, if or secondary role, if any. So that's the first paper that I worked on. And then thankfully, after that paper was published, there was considerable sort of conversation in the literature after, and a lot of this tells us that there's still a lot of work to be done to really understand this, but I'm really, really happy that it got some things. Now, the next paper in my PhD I published was on the radial acceleration relation, and I showed that this relationship can come out of a lambda plus cold dark matter simulation. These simulations are run with this lambda cold dark matter model. However, this radial acceleration relation was actually first sort of theorized to be connected to MON, which is the modified Newtonian dynamics, which tries to describe the universe without the use of dark matter. So what this paper shows, I used simulations to show that this radial acceleration relation can come out of lambda CDM models. And I also show that there are these sort of hooks that come out of the simulations that we should expect to see in low mass galaxies. And we also show that those hooks exist in some of the observed real galaxies today.
Francisco, are the gray in there, is that
Yeah,
observational
so
data, and then the
gray
color
is-
is your simulation?
The gray in the background is the observational data, the colors of the simulations lay right on top of each other, which is really fantastic, super great to see. So that's sort of a paper, again, I can get into this if you're interested after, but I do want to focus on some of the more recent work. But again, the sort of premise of this paper is that this radial acceleration relation arises as a result of a competition between these feedback processes that I've been talking about and sort of the gravity that a galaxy provides. And again, this is due to nature, right? The nature of the internal processes of the galaxies. So I want to just give a quick summary of what I've done in the past for this question of nature. Right? These internal processes are actually what shape the galaxy's gradient strength galaxy age relation and the radial acceleration relation, such that the gradient strength relation shows that galaxies that have older populations of stars tend to have stronger or steeper metallicity gradients, and the radial acceleration relation arises from the interplay between baryonic feedback and the gravitational effects of the underlying dark matter distribution. Any deviations from this are not predicted by MON, but we do see them and we expect to see them in lambda CDM. I want to pause here before I move on. If there are any questions here, I'd like to take them before I move on to the next portion of my talk. Any questions about this?
So are the MON and the dark matter still both are well in the game, or like one is more, one is less?
Sorry, you mean like which ones?
Yeah, I mean
Which-
the theoretical prediction from MON versus the cold dark matter. They are both are still alive, healthy.
Yes.
And
Yes.
or do you say like one is like less and one is more?
Yeah, so in this, they're both absolutely very still alive. And so I just showed using specific simulations that this can come out of the dark matter sort of paradigm. And we expect to see deviations, and we actually do see these in the real observed data We expect to see that in lambda CDM, but that's not expected in MOND, at least in certain models of MOND.
So you said MOND is what you use to measure to fit the RAR appearance for galaxies that have visited feedback from glucose in their profiles. Yes, I'm reading that off the screen. And you said it doesn't account for dark matter, right?
So MOND is an attempt to describe the universe without dark matter.
Okay.
And so you can come up with a framework to predict that radial acceleration relation through MOND. And so that's why this relationship has been used as sort of evidence in support of MOND. What I've done is I've shown that this can come out of lines, right? I wouldn't say it automatically completely kills MOND, but I think it shows some pretty strong evidence for this.
That makes sense. So it just basically assumes, and I hate to reiterate, it basically assumes that dark matter is not a radiation.
Yeah.
Okay.
Excellent question again.
Yeah, so if the internal process is always possible, what would be the alternative? I just look for internal. I would think the effects from dark matter wouldn't that be external?
That's a good question. Yeah, so what is considered internal versus external? I would say that at least for these two scaling relations, a lot of it comes from sort of a feedback of stars. If you would not have that feedback included in the model, you might not see the same relationship. So that's why I say this is not internal. External would be something like interactions with its environment of the galaxy.
So when you say the stellar or environment, and which the dark matter the environment will be the regular mass.
Yeah, so-
Regular galaxies also in the environment.
Right. So I consider all of the dark matter within the galaxy still part of the internal internal makeup of the galaxy, right? The gravity that the dark matter provides is part of the internal properties that are.
Okay, so I still don't understand how you separate internal from external.
Yeah, I think that's based on just the definition that I'm giving. That's how I am taking it to be internal. I'm defining in these projects that internal processes are substitution. They are the gravitational effects caused by the distribution of dark matter within the galaxy.
So external would imply interaction with a different galaxy.
Yeah, so you can imagine like for the gradient strength galaxy age relation, you can imagine a low mass galaxy that was a satellite of a more massive galaxy, right? The effects that satellite feels from its more massive host would be an external process, right? It would be an external.
You mentioning that the attempt of describing the universe without dark matter interests me. What is the implication if that is proven to be true? What is the implication of our universe not having dark matter?
Yeah, I think that's a big question that like MOND is attempting to answer, right? What sorts of things change in the universe if we don't have any dark matter? One of those sort of observable things here is the radial acceleration relation that's been used to sort of argue that, hey, this thing should come out, but we don't expect to see it in lambda CDM. What my paper does is say, no, we can actually see it in lambda CDM. I saw this.
Just want to add to her answer. What would change is basically how you describe gravity. That's what it's going to do.
So one more question.
I'm sorry, I completely forgot. Did you say dark matter or energy?
Dark matter.
Dark matter, okay. Okay, never mind. My question is pertaining to that then.
All right, just for the sake of time, I'm gonna move on and talk a little bit about now some current work. Rather than using these sort of zoomed in simulations to understand how environment affects a galaxy's interior, right now I decided to start using a large volume simulation to determine this question of inertia, right? So now, rather than focusing on one massive galaxy with a few sort of companions, now I'm actually using a simulation that actually contains a large portion of the universe. So this simulation is a firebox. And so it uses the same sophisticated physics that Fire2 zoom-in simulations use. So we still sort of are able to resolve the interstellar medium in galaxies. However, now we have a larger box of about 22.1 co-moving megaparsecs, and we're able to do this work with better statistics, right? So we're using the same amazing physics but now doing better statistics here. And so this is the simulation that I use to think about the nurture aspect of galaxy formation, right? So this simulation resolves about 1,000 galaxies greater than stellar mass 10 to the 8 at resolutions comparable to some of the zoom-ins that we started seeing or that we saw earlier. And so what this simulation looks like in comparison to other simulations are we can sort of plot the spatial resolution of the simulation as a function of the box size of it. And so you can see how many simulations lie in one of two sort of regions. You get the zoom-in simulations that sort of get a lot of spatial resolution, but don't really have a large box size. Or you can have what we see in things like the illustrious simulations, which you have massive boxes, but then the trade-off is that you get sort of less or worse spatial resolution, right? Firebox sits up here, right? So it's a very happy medium. You get sort of a greater dynamical range compared to both the zoom and the large volume. So it's a very, very great tool to use to answer these kinds of questions of how a galaxy's radiant environment affects its interiors. So I specifically have recently worked with two scaling relations for specifically low mass galaxies. So these are galaxies with stellar mass of less than 10 to the 9 solar masses. The left one here is the half mass radius, or sort of the size of the galaxy. This is the half mass radius of the stars as a function of the stellar mass of a galaxy. So you see that we've got a relationship such that more massive galaxies will be larger. The other scaling relation I look at here is the inner dark matter mass. So this is the mass within the half mass radius over here as a function of the stellar mass. And so the color code here just corresponds to how far away each point is from the average and the median behavior of the galaxies. Now the circles here are centrals, which just means that it is a galaxy by itself. It is not a satellite of another galaxy. The triangles are the opposite. These are satellites that are orbiting, right, another, or are gravitationally bound to another galaxy. So you can see that you have satellites that exist up here. You also have some satellites that exist down there. And so the question that I want to ask is, how does environment, at fixed mass, how does environment affect whether a galaxy is below or above these relations? Right? Is a galaxy more red if it is in a denser region of the universe? Is it more blue? Right? How does environment really affect a galaxy's position on the scale? Right? That's the question that I would like. Now, to do this, we had to actually quantify what environment is, right? How do we actually determine, how do we say that a galaxy is in a denser region or not? For that, I use the perturbation index, which is a metric that's generally used in the literature to determine how perturbed a galaxy is due to its companions. The definition of this is just the ratio of a galaxy's tidal force to its binding force. So you get something like this on the right-hand side if you use the virial mass and the virial radius, right? The mass and the size of a galaxy, as well as its distance to a companion. You can get the sort of perturbation that a perturbation on a galaxy due to a companion. Now you can add all of the sort of perturbation indices on a galaxy due to many companions, right? Some k nearest neighbors within some box are max to get really the effect of a galaxy's environment on itself, right? And so with this project, we consider all of the companions in the box just to see what the effect from everything around it is on a galaxy. So what we get is that a higher PI, a higher perturbation index, means that a galaxy is more perturbed by its environment. Right? It's got some more massive galaxies nearby that are affecting it. A lower PI just means that maybe it's in a little bit of a more isolated region. So I use PI to really quantify the galaxy's environment. So what you see here is I am plotting the scaling relations that we saw before. However, now I'm plotting the median behavior of galaxies with high PI in purple and low PI in green, right? So what this is showing is that the galaxies that are in more dense environments that are being more perturbed by its companions are in purple, while the others are in green. And what we see is that at least for the size-mass relation here, at fixed stellar mass, galaxies that reside in, or galaxies that are more perturbed by its environment will generally be larger, will be more, it'll be sort of larger compared to other galaxies of the same stellar mass. In the middle here is the second scaling relation, the inner dark matter mass is a function of stellar mass. And you see that they kind of overlap mostly, and you really see if there's any difference at all, you might see a little bit at the lowest mass regions, which kind of makes sense. At the lowest mass regions is where the sort of internal effects of star formation really affect the galaxy more. So you might see that difference there. That might be what this is. Now on the right is a different scaling relation that many folks in the field use. It's generally the stellar mass halo mass relation, but here I've inverted it because we're looking at everything at fixed stellar mass. And what we see here is that if you look at that scaling relation, you also see that galaxies that are more perturbed by their environment generally have lower virial masses, right? They sit lower compared to galaxies that are less perturbed at fixed stellar masses. So we see this sort of effect coming up here.
Comedian was named Iglesias, you know, like, I'm not fat, I'm fluffy.
I'm not fat, I'm fluffy.
That's what the left one panel reminds me.
Mhm. Yeah, they're definitely like more extended, right? You can have the same stellar mass but have different sizes, and it turns out that the environment can help predict how extended, how fluffy a galaxy is, right? So as I've already mentioned, at fixed stellar mass, galaxies with higher PI tend to be more extended and have lower virial masses. Now this is kind of just qualitatively looking at what this looks like at fixed stellar mass. But now what we can actually do is plot, again, if you remember what this delta log was, it's really just the log distance from the average relation on these scaling relations. You can plot that as a function of PI, it's a function of environment. And so what we see is that for the size mass relation, again, higher PI values will give you a higher delta log value, right? You will be more extended compared to other galaxies in the same mass. And then as we sort of alluded to earlier, for this dark matter mass in the inner region, you don't really see much of an effect until you get to the highest PI values. And it turns out that the galaxies that have these highest PI values are these sort of satellites at lower masses, right? So they can be more, their inner dark matter mass can be more affected by their environment at these lowest masses. And then finally, at the very end, you can see, again, this same relationship between how far a galaxy is from the virial mass stellar mass relation as a function of PI, and you can really see this strong drop off as you go to higher PIs. So it's interesting to see that we see this relationship between environment and where a galaxy lies at a fixed mass for all of these scaling relations. But then the next question is environment the only thing playing a role here, right? What else can be affecting these scaling relations? And for that, I use what we call a random forest regression. This is a machine learning technique that is used in the field to sort of predict, in this case, we are doing some regression, you can predict some property using a series of a bunch of decision trees. And so what's really nice about random forest is that you can train this model on a bunch of subsets, a bunch of random subsets of this data. And at the end of the training, all of these trees can vote to predict a given value. So let's say we want to predict the temperature on a certain day, right? So we want to say, what would be the temperature today? We could feed this model a bunch of different days. We can feed it the air pressure. We can feed it what the day of the week is. We can feed it the average temperature. And then we can feed it like what month it is, right? And so you can kind of tell from here that some of these might not be as important. Maybe the day of the week is not as important in determining what the temperature is, right? So the trees that have this day of the week involved in that decision tree might not do as well. But that's where this voting comes in handy, right? All of these trees, regardless of how well they perform, the ones that perform most will really help you predict this temperature. So I use this regression model to try to predict how far away from the average relation these galaxies lie. So I feed the virial mass, this PI value that I've been talking about, and then the fraction of gas within the galaxy to predict these two values, right? I want to predict either how far away, how sort of puffy, how fluffy or extended the galaxy is, and I also want to predict maybe how dark matter rich or dark matter poor galaxy is given these three features. What's also really great about this random forest regression compared to the other machine learning models is that it's not a black box. You can actually print out each of these trees and see what it's doing. And again, as I mentioned in the sort of analogy for the temperature, you can see from the trees that maybe the day of the week is not a really important feature to predict temperature. And we can do that here. And so what I do is I figure out what features are most important in predicting this sort of fluffiness or dark matter richness. Right? That's the question that I asked. And so to do that, I can show this is in order of importance. So I can actually plot the feature importance from these models. And we see that the most important thing to predict this sort of puffiness is a variable mass, but it's also affected by the environment and somewhat the gas fraction, right? Well, what if we want to look at the other thing that we're trying to predict, right? That dark matter inner region, right? That dark matter mass. Well, that one really is dependent on variable mass, and there's very little importance on the two other features. So this is showing a couple of examples of something that's not right. The environment does play a role in setting the relative size of the galaxy, right? But also involves variable mass and also involves gas fraction. So there's a bunch of things going on that really set a galaxy's position on that scaling relation. But if we look at the dark matter mass, excuse me, the inner dark matter mass, variable mass really is what's the best predictor for that.
Are you showing correlations or causality? Either could give you this.
Yeah. So I think that's a really good question. To me, I think this is a correlation, but it doesn't necessarily mean that it's being caused by this. So I'm interested in eventually helping observers be able to tell if you can understand what the properties of a given galaxy is. Maybe you can predict how extended it will be compared to others, right? At a given time, right? But this is not implying any causation between these things. So yeah, as I mentioned, variable mass is the best predictor for both of these things, right? But for the size of a galaxy, there are multiple things happening, multiple factors at play. Again, galaxy formation is very complex, it's very complicated, and this is really showing that. I think it's really cool. So I just want to show how important the variable mass is in setting this sort of delta log R and delta log MDM. Right? You can really see that galaxies are more extended for galaxies that have lower variable masses, and this is the same regardless of how you split up the populations. So if you split up the populations in terms of central galaxies and satellite galaxies, follows this relationship as well as the other, right? You have galaxies that are more dark matter poor in their inner regions, or galaxies that have lower variable mass.
It might be helpful for especially some of the younger students in the room. Can you define variable mass for them?
Yeah. So variable mass, I like to think about it as it's a measure of the mass in dark matter that a galaxy has. There's a sort of straight definition of it, having to do with the cosmology that you're using. But at its base, I like to think about it as sort of the total dark matter gas that belongs to a galaxy. So as I said, regardless of how you split up these populations, it shows that variable mass is very important in determining whether a galaxy is extended, whether it's dark matter rich or dark matter poor. You could also split it up in terms of environment, right? So this is the same exact thing, except now I'm splitting it in terms of high PI values and low PI values, and you still see that the galaxies follow this relationship here such that galaxies with lower variable mass will be puffier, will be more extended, and dark matter poor in the regions. So all this to say is that at least for the size of a galaxy, the relative size of a galaxy, there's a lot going on. And so I attempt to show that in this plot here. So there's a lot happening in this plot. I'm going to walk you all through it. This is on the y-axis, the variable mass of a galaxy. On the x-axis is the stellar mass. This is a very common relationship shown in galaxy formation. And all of these points have different colors corresponding to their environments. So a red point here corresponds to a galaxy that is more perturbed by its environment. Blue ones are less perturbed. And then finally, the size is tied to the relative size of a galaxy at fixed stellar mass. So what that means is that the larger points are galaxies that are more extended compared to other galaxies of the same mass. And so what we see is that you can have large or extended galaxies if, whoops. Sorry about that. Here we go. You can have large and extended galaxies if you have a low virial mass, right, at fixed stellar mass, and you live in an environment where you are more perturbed by your environment, right? So if you have a low virial mass compared to other galaxies of the same mass, you are more susceptible to being affected by your environment. And so if you are affected, you end up with a larger relative size. That's why we see all of these, a bunch of large points down here. And so this is sort of a way to show that there are multiple things happening here. This, of course, does not describe the full extent of what might be affecting this, but I think it's an answer, and it's a small answer to what might be going on in setting the relative size of galaxies. Now, here we go. Okay, I do want to talk a little bit about another project that I'm working on having to do with environment, and that is with a student at Pomona College. His name is Brian Gerard, and he is working on determining how environment affects a galaxy's formation times. So he does this using star formation histories of a galaxy. So if you take a galaxy, you take all of its stars and you bin them in terms of age, you can sort of track sort of the history of star formation of the galaxy, so that at 14 billion years after the Big Bang, you arrive at what the galaxy's stellar mass is today, right? And so you can actually find out when a star formed 30%, or sorry, when the galaxy formed 30% of stars, when it formed 50%, and when it formed 90%. And so these are sort of quantities that we use to sort of gauge a galaxy's time scale, its formation time scale. And Brian plotted made very similar plots to the ones that I've just shown you, where he plots the 30th percentile stars, the stars, 50th percentile, and 90. So when a galaxy formed 30, 50, and 90% of its stars, and found that there is a positive relationship between a galaxy's, what we call tau 30, and its environment. Right? So what this is saying is that galaxies that are more affected by their environment have later star formation, or they form 30% of their stars later in their lifetime when compared to galaxies that are less affected. And this relationship still kind of exists in this T50 space, but once you get to 290, pretty much all of the galaxies in this sample formed 90% of their stars very recent, right? There's actually kind of a slight drop off here, but it's pretty flat. So it's really interesting that depending on what quantity you choose, there's a different relationship.
How are you able to tell how old the star or galaxy is? Because I ask because of the way light travels. How would you be able to tell how old the galaxy is simply based off of just knowing how far away it is?
Yeah, that's a good question. So the question was, how can we tell how old a star is, right?
Yeah, exactly.
Depending
Count
on
by light years.
Yeah, so I think what really helps us is sort of the chemistry and color of the star. That really helps us determine how old a star is, right? You can take what we call a color magnitude diagram, right, and see where a star is on that color magnitude diagram, or on its what we call an isochrone as it evolves over time, and we can estimate how old it is from that.
So the distance is not accounted for in determining the age of a star. So
And
it's
then-
only relative to us. Okay.
And so for these simulations, we have all the information coded in. We have the age of the star, so we don't really need to do all of that manually.
I'm sorry, I just have, in case we do get interrupted, I want you to be able to go the whole time. I forgot to mention, at 12:15, there'll be pizza for students with Dr. Mercado in 2011. Okay, thank you, sorry.
Awesome, thank you for that. So now I want to just give a brief summary of sort of the nature aspect of my work. Right, environment does play a role in determining both the galaxy's relative size, as well as, at fixed stellar mass. And it's not the only factor at play here, right? We talked a little bit about how virial mass is also very important. From Brian's project, we do see that environment also plays a role in setting a galaxy's formation time. We still have a little bit more work to do there, but I think it was really cool showing some of his initial results here. Doing this work is really important, especially in this sort of era of astronomy where we're with new telescopes like the Vera C. Rubin Observatory. We're going to be discovering many, many new low mass galaxies in different environments. So really understanding how the environment really affects small galaxies like that is very important at this time. So I'm really excited for the time that we are in. So I think we do have like a few minutes to talk a little bit about some of the work that I'm doing in sort of the broader impacts area of my NSF fellowship. So we've been talking about galaxies and nature versus nurture, right? I'm very, very passionate about nurturing young scientists and really uplifting marginalized scientists in the field. So what I propose to do for this project is I propose to teach an Astro 2 class at Pomona College. This is a galaxies and cosmology class. And aside from learning about galaxies and cosmology, we also discussed how astronomers, academics, scientists are people first. And in that class, once a week, we held community justice discussions. And these discussions revolved around issues affecting both marginalized people in astronomy and physics. This is a joint physics and astronomy department, so we also talk a little bit about physics, and also in the wider scientific community. And so what this entailed was students would read an article every week. We would come together and discuss it. So some of these articles had to do with issues like maybe the TMT you all might have heard of has sparked some kind of controversy in the past few years. We talked a little bit about imposter syndrome as well. And so many of these things that affect marginalized astronomers and physicists and scientists in general, we discussed in this class. And what was really great about this is that this class culminated in what I call the Astronomy project. What this was is that this was a group project at the end of the semester where students all got together into groups and they did research on astronomical discoveries by marginalized scientists in the field, and also methods to dismantle barriers operating against marginalized communities. And so they did these group presentations at the end. My favorite part of this, and it seems like the favorite part of the students, were that they got to meet actual astronomers in the field. They got to interview them, and they presented on one, their sort of path in the field, and two, what research they did. So their presentations at the end talked about these astronomers as people. They also talked about their science and their contributions to the field, many of which contribute to what we learned in class, which is really, really awesome. Further down the line, all of these projects are going to be used as a basis for planetarium shows that will be shown at Pomona College. So I'm currently working with Pomona College planetarium staff to take all of the sort of work that students did in sort of curating all of this information and making planetarium shows that sit at the intersection of science and business. So I'm really, really excited about this. Again, this is built from content that the students created. I'm really, really excited about this. Hopefully we will in the next year start the pilot program for this, and you will all hear about that hopefully once we start showing those shows. I think I am pretty much at time, so I want to sort of go here. I'll give a little bit of a summary, but thank you all so much for having me.
The fire alarm will lose it.
It doesn't happen.
I didn't say the pizza thing because you wouldn't be able to hear me.
Yeah. Yeah, pizza 12:15.
So how big a computer you need to run your simulations?
Yeah, so these simulations cannot be run on any like laptop, right? So these simulations are run on supercomputers, hosted by NASA, hosted by different universities. And so I would say it's simple, right? Zoom-in simulation that's sort of tracking the formation of a Milky Way-like galaxy could take up to 6 months to run, right? On a supercomputer. So it's nuts how much it's for. Question back there?
When like starting a research project like this, what are the steps to getting your idea? What made you go, this is what I want to research, and this is the steps I'm taking?
That's a really great question. So to be completely honest, when I started my PhD, I was nowhere near thinking about sort of unique science ideas. At the time, I was like, I kind of like simulations, I like galaxies, and my PhD advisor was like, here are some projects. projects, right, that you would watch. Those are sort of the projects that I worked on. As I sort of went through my PhD, I started understanding the field a little bit better. I started sort of thinking of my own ideas, and there are just sort of questions that come up, right? If you have, I have these tools I'm thinking about. I have these tools. I have this question about galaxy formation that has not really been answered yet. Why not try out a project? Sometimes it might not pan out. Sometimes it will. But that's just
Did you have any projects or concepts that didn't pan out that kind of failed, or you were like, oh, that's not the kind of output I was looking for?
Yeah. So I think like one of the first projects that I did at UC Irvine, we were trying to run simulations of just what we call an ideal. Anyway, I just thought it was.
All right.
Keep coffee outside.
So everyone go to the stairwell, no elevator, walk out to the, maybe in front of the building gate is where we end up gathering.